Hi guys, and welcome back. So, brand new topic, not really much to say to start off. Two different ideas that we're talking about today, areas of regular polygons and also of composite figures. So it is going to be some brand new information. It is a brand new section. It's section 11.4 if you guys need to find any additional information about it. But let's just kind of jump right into it. So I think we all know what a regular polygon is. If you guys don't remember, it is a polygon with all sides congruent and all angles congruent. So like this pentagon down here. This first part I think is pretty self-explanatory. The center of a regular polygon is equidistant from the vertices. So in this case, the center would be C. I think you guys remember, I think you guys might remember how to figure out the central angle of a regular. Oh no, this is different. All right, I'm thinking about something else. Sorry, I'm thinking about like these angles up here. We talked about that. All right. This idea here is, it says right here, a central angle of a regular polygon has its vertex at the center and its sides pass through consecutive vertices. So if we use this picture for reference, GCH would be an example of a central angle in the regular polygon. HCD would be another one, DCE, etc., etc. All right. I was thinking a little bit ahead about how you would find like GHD, one of the angles in the pentagon itself, which we did talk about like around wintertime. I think that was sometime in chapter 6. Before you guys ask, and like this will all make more sense once we get to some things in a little bit. If you remember the formula to find the measure of one angle in a regular polygon to find GHD, you could absolutely use that. If that makes more sense to you. I don't know which one I'm going to do yet. I'll see how I feel. But here's your formula to find the measure of the central angle. So like the measure of angle GCH would be 360 over n, where n still represents how many sides you have in the polygon. All right, and I know I skipped over this apothem thing, which is brand new. And all the apothem is, it's the distance from the center to any side of the polygon. All right. So again, if we use this pentagon for reference, CB would be an example of an apothem. All right. It is important to note that CB, this apothem, is perpendicular to the side FE. When we find the areas of these kinds of polygons in a little bit, that is going to be really, really important. All right. So again, just kind of example of what's going on here. This pentagon has a center at C, apothem BC, and central angle DCE. All right, so just some really quick practice with that before we get into all of this. Where this comes from is the fact that you can inscribe all kinds of polygons inside a circle. There's a lot more information about that in the textbook. But I just kind of want to get used to finding all of this information before we get going. All right. The center, I'm going to write that down. The center is going to be X. We can also tell that because of the fact that we're talking about being inscribed in circle X. Circles are named by their centers. Ooh, wow. So this is point X for the center. A radius, well, we know what the radius is. It's going to be any segment from the center to the edge of the circle. So one radius would be XQ. Another one would be XR. You could even draw more in XS, XT, XP. All of those are radii. But the apothem is, again, that's a little bit more specific. It's the distance from the center of the circle / the center of the polygon to the edge of the polygon. So the only apothem that's pointed out in this picture is XN. All right. What else? All right. A central angle. Again, a central angle has to have its vertex at the center. So the only one that's pointed out in this picture is angle QXR from here to here to here. All right. Again, you can draw more if you want. there's plenty of central angles here, but we're just going to focus on the one. The measure of that central angle, so the measure of angle QXR is 360 over n, where n is the number of sides. So since this is a pentagon, this is 360 over 5, which is 72, I think. Whoops. Punching that in my calculator. Yep. 360 over 5 is 72 degrees. So that's the measure of angle QXR. All right. Just some basics before we get into the actual area stuff, because this is a formula for the area of a regular polygon. All right. It doesn't matter how many sides the polygon has. It could have 5 sides. It could have 6 sides. It could have 187 sides. The formula is going to be exactly the same. All right. The area of a regular polygon with side length S is 1/2 of the product of the apothem and the perimeter. So I usually stick with this formula, 1/2 AP. I'm going to use that a lot more. You'll probably see that a lot more frequently in resources on the internet, in the textbook. I'm sure you're able to figure out that there's going to be a little bit more work that we would need to do to get all of that information before we actually plug it into the formula. All right. So this 5, that's right here, is talking about the length of QR. All right. So that's going to help us a lot with some of it. If we have one side length of 5, because it's regular, whoops, we know all the side lengths are going to be the same. All right. So the perimeter is just going to be that length 5 times the 6 sides, which is 30. All right. But we still need the apothem. All right. How is that going to help? All right. Or how are we going to get that? That's why we started talking about like the central angle business before. All right. QPR is a central angle in the hexagon. All right, so the measure of angle QPR is going to be 360 over 6, because there's 6 sides in a hexagon. So I'm going to write that down. The measure of angle QPR is 360 over 6, which is 60. So this is 60 degrees. All right, because it's a regular polygon, we are also, like, there's a couple things you can say here. All right. We know PS, because it's a regular polygon, this triangle inside we can also deduce to be regular. All right, so there's a couple things you could say. If this angle is 60, all the angles in the triangle are 60. You know? Or at least these two angles are going to be congruent. You know, and if one is 60, I think we know how to find the other two angles by now. You know? All right? So then, one of the other things we could also say, even if those numbers change a bunch, is the fact that this 60 up here, PS splits the 60 in half. So this is 30, QPS is 30, and RPS is 30. And I think you guys kind of know, hopefully, where this is going. This is a 30, 60, 90 triangle. All right, I'm actually going to draw that 30, 60, 90 triangle again down here just for the sake of organization. This is 60, this is 30. We had this entire length as 5, so there's a couple of things you could say. All right, you could say this is 2.5 to split it up. We have that the triangle QPR inside is equilateral, which means all the sides are the same, so the hypotenuse is going to be 5. And the important thing is the fact that we're using our 30, 60, 90 rules. All right, so 30, 60, 90 rules, again, go in terms of your short leg, or it's all in terms of your short leg, which is right here. And your long leg, which is opposite the 60, is your short leg times root 3. All right, so your long leg here is, going to be 2.5 times root 3. And that, if you go back to the picture, is PS, which is our apothem. All right, so I'm going to just make another separate note of that. Okay. All right. So now that we have the apothem and the perimeter, now we're able to use the 1/2 AP formula to figure out the actual area of the hexagon. All right, so the area is 1/2 times the apothem, which is 2.5 root 3, times the perimeter, which we got earlier, is 30. All right, and it does say round to the nearest tenth, so I'm actually just going to plug all of this into my calculator and then round it off. So 0.5 times 2.5 root 3 times 30. Make sure you leave the radical, like hit that right arrow so you get out of the radical if you're plugging all this in your calculator. So we get that mess. We're going to round to the nearest tenth. So the 5 pushes the 9 up to the 0, which pushes the 4 up to the 5. All right, so in short, the area of the hexagon is approximately, you know what, I'll actually do approximately, 65.0 or 65, what are the units? Meters squared. Okay? Let's do another one. All right. So, find the area of the regular pentagon. All right. I think this is going to be a little bit different just because we have the 9 here. All right. Let's actually do the central angle first. All right. We have this as a pentagon. So we did that earlier. 360 divided by 5, the measure of the central angle, which is ACB, is 72. All right. If we know CB is 9, CA is also going to be 9. Which means angle A and angle B, or angle CAD and CBD, these two right here are going to be congruent. They're not also going to be 72 because that doesn't work. That's not how triangles work. Let's see. 180 minus 72 divided by 2. Both of these angles in here are going to be 54. All right. So we have the 90 right here, so that's going to help. We could easily split the 72 up into 36 and 36. But this is a little bit different because you guys are going to have to use trig for this problem. All right. We don't know anything about like a special relationship between like 36, 54, 90 triangles or anything like that. So we're just going to have to go back to trigonometry to not only find the apothem CD, but to find BD, and then by consequence, the whole length of the side. All right, so I'm actually going to, again, draw this triangle down here. So this is 54, and we know this is 9. All right, so let's say we want to find the apothem first. All right, like we'll call this X, okay? X is opposite the 54 degree angle, and 9 is our hypotenuse. So opposite and hypotenuse goes with sine. So I'm actually going to rename this A for the apothem. So the sine of 54 is opposite over hypotenuse. So A over 9, multiply both sides by 9. And then if we plug this into the calculator, let me just make sure. Degree mode, cool. 9 times the sine of 54 is approximately 7.28. All right. Now, if we call, let's say we'll call this B, right? B then is adjacent, and if we're still dealing with the adjacent and our hypotenuse, because again, if you go all the way back to trig stuff, which I think was chapter 8, my suggestion to you about that was using your given values for the sake of consistency and making sure you're getting all the right numbers. Because let's say if this 7.28 is wrong or just a little bit off, it's going to mess everything up. So adjacent and hypotenuse is cosine this time. So the cosine of 54 is B over 9. So this is 9 times the cosine of 54, which is about 5.29. So I want to go back to this picture for a second. All right, 5.29 was B, which if you go back here, represents BD. All right, But BD is not the full side of the pentagon, all right? It's AB. If we know, though, that these are congruent, all right, the angles are also congruent, and then AD and BD are congruent. You know, kind of like proving triangles congruent and stuff like that, if you guys remember that. Hypotenuse leg or something like that. I think that's how you'd prove these triangles congruent. Anyway, if this is approximately 5.29, AD is also approximately 5.29, which means you can double 5.29 to get the full length of the side. All right? So I kept that long decimal in my calculator so I knew my approximation wouldn't throw anything off. So AB, or any side length, I'm just going to write it here for the sake of space, is approximately 10.58. All right? Again, it's a regular polygon, so all sides are the same. So if one side is 10.58, the perimeter is times 5. So the perimeter is approximately 52.9. You can't see that. 52.9. All right? So if we use all this, all right, let's see. Again, this is the formula for the area of the polygon. So now we have all that, all right? We had our apothem earlier with 7.28. Perimeter is 52.9. So 1/2 times 7.28 times 52.9 is approximately, we'll keep the 52.9 in there, times 0.5 times 7.28. So this might not be the most accurate, but if we round this off to the nearest decimal, or to the nearest tenth, like it asks us to, this is approximately 192.6 centimeters squared. I just want to see really quick while we're here. So 9 cosine of 54. If I leave everything, what I'm doing is if I leave everything in the calculator, will I still get approximately the same thing? So that was our half the side times 2 times 5. That's the perimeter. And then we plugged this into the calculator to get the apothem approximately. So if I do times 9 times the sine of 54, and then divide that by 2. Oh, cool. It does still get us approximately 192.6. Nice. So that's our final answer. Okay? All right. So I think I will actually draw an octagon really quick so we know what octagons look like. They kind of look like that. Mine's really ugly, but it's fine. The side length is 4. So that makes our life a lot easier. If we have the side length, we can find the perimeter. 8 sides, 4 times 8 is 32. So if we place our center here, here's our apothem, and there's our central angle. So again, I'm going to redraw this triangle down here. The measure of that central angle is 360 divided by 8. By 8, which is 45. All right. So if that's the case, these two other angles are 180 minus 45 divided by 2. So these are both about 67.5. If this is 4, each piece is 2. So we only need the apothem, all right, because we already got the perimeter. So again, we can use trig for this, all right? This 2 right here is adjacent to the 67.5, and the apothem is opposite. So opposite and adjacent is tangent. So tangent of 67.5 is equal to, again, we'll call this A for apothem, opposite over adjacent. So A over 2. A is 2 times tangent of 67.5. Which is 4.83 approximately. I'm going to leave this in my calculator for rounding's sake and for consistency's sake, because 32 is pretty nice. The area is still going to be 1/2 times the apothem times the perimeter. So it's 1/2 times this, about 4.83 times 32. So this is getting divided by 2, and it's also being multiplied by 32. So rounded to the nearest 10th, let's say, again, is approximately 77.3 centimeters squared, because that was our unit. Okay? All right. So that is it for area of regular polygons. This is probably going to be a really long video because there are 2 big things that we're talking about. A composite figure, I think, is going to be a lot more straightforward. A composite figure is a figure that can be separated into regions that are basic figures, such as triangles, rectangles, trapezoids, and circles. To find the area of a composite figure, find the area of each basic figure, and then use the area addition postulate to add them together. So basically, you are just finding the area of each piece and then adding them all up. So, in this picture, we have, technically, if you wanted to, you could draw another line and split this down into not only a semicircle, but a rectangle and a triangle. All right, but it is also a trapezoid. All right, so since we're over 20 minutes now, just to kind of do this a little bit quicker, we're only going to split it into a semicircle and a trapezoid. All right. Trapezoid, we just did that in the last video. The area of a trapezoid is 1/2 times the sum of the bases times the height. So these are our 2 bases of the trapezoid. So it's 1/2 times 20 plus 32 times the height, which is 14. So times 14. There we go. So the area of the trapezoid is 364 millimeters. Now here's the thing. I said semicircle. All right. So this is only half a circle. We know the area for a circle is going to be pi r squared. But because it's just a semicircle, we have to cut it in half. All right. So that's what we got to do in this case. The radius also, like the 20 right here, is from end to end, so it's the diameter. So the radius is actually going to be 10. So this is pi times 10 squared over 2. So this is 100 over 2. This is 50 pi. All right? So then the area of the whole figure is you're just taking those 2 things and you're adding them together. 364 plus 50 pi millimeters squared. If the question asked you for an exact answer, this is what I would be looking for. But since it does say round to the nearest 10th, we can plug that into our calculator and get an approximation, which is about 521.1 millimeters squared. Okay? All right. Now, there's a lot that you could do here, all right? Let me actually get another pen. Here's my pen. Okay. I mean, at first glance, I think you guys might see like 4 figures here, right? There's this triangle right here, there's this trapezoid, there's this triangle, and there's this triangle, all right? But finding the measurements of all those individual pieces to get the actual area is, I'm telling you, going to be super, super complicated. So what I also see is, I'm going to do this like as lightly as I can just so I can still get the information. We have these 2 parallel sides. All right. So this whole thing that I'm going to shade a little bit in blue is a parallelogram. All right. And then we can consider the rest of it, this incorporating the entire 5 and the 10. That's a whole triangle. So if we just do the area of that parallelogram in blue plus the area of that triangle in black, it's going to make our lives a whole lot easier, especially because we have all of the information. the area of a parallelogram is the base times height. And we have that the entire base is 8 and the entire height is 5. So the area of the parallelogram is going to be 40, let me mark that off, feet squared. Triangle is half base times height. And again, we have the entire 10 and the entire 5. So half of 5 times 10 is 25 feet squared. And then the area of the whole thing is just the sum of those two pieces of information. 40 plus 25 is 65. And that's it. Here, it says shaded area, all right? I think it says shaded area for the last few, but the shaded area was the entire thing, all right? The shaded area now is the area of this entire triangle, except for this semicircle. So what we're gonna do is find the area of the triangle and the semicircle, and then instead of adding them, we're going to subtract them, all right? Because this is a whole. So this is a right triangle, so the actual measurements that we need are pretty much given to us, the 26 and the 18. So the area of the triangle is 1/2 times 26 times 18, which is 234. And again, semicircle. So we're going to take pi r squared and we're going to cut it in half. 9 again is from end to end, so it's our diameter, which means our radius is 4.5. So if I leave it in terms of pi for now, 4.5 squared is 20.25, divided by 2 is 10.125. So the area exactly is 10.125. And again, the area of the shaded region is the difference between the triangle and that semicircle. So if we left it exact, it would be 234 minus 10.125 pi. But again, because it says to round to the nearest tenth, we are going to plug that all into our calculator. So 234 minus 10.125 pi is approximately 202.2 feet squared. Cool. Last one. I know it's a little bit hard to see, but this all right here is in green. All right, like these 4 pieces. Okay. It's a circle. So what we're going to do is we're going to take the area of the circle and then subtract. This is a square in here. All right, if this is the diameter, this is 180, which means these inscribed angles are all right. And you have the tick marks right here. So that's how we know for a fact it's a square. All right, we'll do the area of the circle first because this time it's an entire circle. 6 is our diameter, which means our radius is 3. So the area of the circle is 9 pi. Okay, square this time. All right, if you have these right angles and these congruent tick marks, the angles down here in the actual triangle are congruent, which means if this is 90, this is 45, this is 45. So you've got two 45, 45, 90 triangles, both with the same hypotenuse of 6. All right, and if you remember 45, 45, 90 triangles, I think we talked about it a few days ago. The hypotenuse is the leg times root 2. So if we call the leg x, x times root 2 is our hypotenuse, which is 6. Okay? So x is 6 over root 2. We don't want any radicals in the denominator, so we're going to rationalize. There we go. And that means this is 6 root 2 over 2, which is 3 root 2. Okay? So that is, I'm going to do it here, one side of the square. And we know the area of a square is, you could also say base times height, length times width, or it's also side squared. So 3 root 2 squared. And that squared's got to go to both. All right, so this is 9 times 2, which is 18. So that means the area of the shaded region is the area of the circle minus the area of the square. So 9 pi minus 18 for the exact answer, or as a decimal approximation, is 10.3 inches squared. Okay? And that's it. All right, I know, again, it was pretty long, but this, I think, is slightly more complicated just because it's brand new, or some of it was brand new at least. I think you guys know where to reach me by now if you have any questions, and I'll talk to you guys soon.